guys for? And they are combinational logic, but they have their own unique symbol because we use them so much. So of course that means if we use them that much, they got to be important, right? So what's some of the uses for exclusive ORs and exclusive NORs? In fact, the book gives them a whole chapter on their own, don't they? So one thing we need to understand that exclusive ORs and exclusive NORs will always only have two inputs. And these are the circuits, by the way, that basically make up exclusive ORs and exclusive NORs. And of course, these are the two symbols, right? You understand that? So how many inputs will these guys here have? Two. No more, no less. So when we talk about ANDs and ORs and NANDs and NORs, we say they have a minimum of two, but an exclusive OR will only have two. And what they do is they look for equality. They look for equality on the input. Doing that, they can also do math. They can pair. They can math. We can make what they call programmable inverters. Do a lot of neat stuff. Now, what we look for these things is we look for them. So with this, what this output tells us, it tells us what we get when they are not equal. When they are not equal. So of course we've only got 4 inputs that we can put on, 4 different input combinations we can put on these things, right? And that's it. So this guy tells us what we get when it's not equal. So if that's what we get when it's not equal, then up here we would get a 1 and a 1, and right here we'd get a what? 0 and a 0. Okay, you understand? So if I did the same thing, so that this is in, these are ins and these are outs. If I did the same thing for the exclusive NOR, this says I get a low when they're not equal, so I'd come up and then I'd do that. So what we're saying is that I can look at the output of this gate, not even knowing what the inputs are, and I can tell if the inputs are equal or if the inputs are not equal. You understand that? So if I look at this one and I get a 0, I know the inputs are equal. If I get a 1, I know the inputs are what? Not equal. On this one, of course, it would just be opposite. Here, if I get a 1, we know the inputs are equal. Here we have a 0, we know they're not equal. Now what gets people confused is that when they see that bubble, they say, well, it's true when it's low, and that's true, but remember, it's true when they're not equal. Okay, y'all understand? And then, of course, if it's not true, then we get the opposite state. And we've been doing these for a long, long time, and even in motor controls, y'all run into these exclusive ORs and exclusive NORs, PLCs. We can do this with relays. We can do it with push buttons, but we could also do it with relays. So we can do math with them, because when we add, so if I add a 0 and a 0, what do I get? 0, right? And if I add a 0 and a 1, what do I get? 1. If I add a 1 and a 0, what do I get? 1. If I add a 1, 1, what do I get? I get a 0 with a carry of 1. Okay, y'all, and that's the truth table for that guy right there. All we got to do is take care of the carry, right? You understand that? So if I take care of the carry by coming up here and putting an AND gate, that means that when this goes to, so that would be our 0 with a carry of 1, right? What's that? The thumb drive is over on my computer. That blue thumb drive. And then of course, so we have what we call a half adder. That's what they call a half adder. And then they add a little more circuitry to come up and give us what we call a full adder, which would be this right here. So this guy picks up the carry from the other module. So this would be basically what we use for the least significant bit. And then we take this and feed it into that, then the other two bits, and then we take the carry out and feed it where? To the next one and the next one, and this guy here would do math. So this right here is what we call a full adder, and y'all don't really have to understand how it works. All you need to know right now is these guys do math. Because if I wanted to do a math, I'd go out and buy an adder. So we have integrated circuits that are adders. That's what they do in life. So we can get ICs, but this is what they're made of. So what we're going to do is we're going to start getting into combinational logic. And we're not going to be concerned what makes it up. All we know is the 5 basic gates make up everything, right? You understand? So I got a counter. Well, what makes up the inside of a counter? The 5 basic gates. But they're arranged in a way so I put pulses in and it counts in binary on the output, right? You understand that? We have multiplexers, we have shift registers, we got counters, we got all kind of things we do, but everything's made out of the 5 basic gates. And of course we call this combinational logic. But yeah, we can get an adder. They cover an adder in the book. This is not a good diagram. This is the way that National Semiconductors does that. Most of the chip manufacturers calls one set of inputs the A inputs, and the other set of inputs they call these the B inputs. And then one would be these would be outs. One of them would be, this says that P is greater than Q. Well, what we do is we just come over here and put A on that side, understand, and B on that side. Now this is the way I've seen them. I've never seen one that used this nomenclature for pinouts. And this is a 7485, which is ORI, it's a 4-bit comparator. And if we looked at the if we want to get a feel of what's going on here, let's see if I've got it. I'm going to go to digital, and let's go to graphics. Let's see if we see a 7485 in here or not. We'll look it up on the internet. Sometimes I do things at home, and I forget to upload them to my... Okay, so this is a 74. No, that's what I showed the other day, where they string a bunch of them together. But we'll look at the insides just to get a little feel of what we talk about, combinational logic. Huh? Although I'm just gonna Google it so we can. I'm gonna get the image of it, and that way it'll show us. One of these images will actually be the internals of this thing somewhere. And here it is right here. Okay, so this is the internals of that thing. But there it is right there. That's the circuit I put. I don't know if y'all see it or not, but I have to go back to my PowerPoints and show you the circuit of a comparator, which would be this circuit right there, and there they are. And that's the same circuit, right? You'll see that. Huh? This is it's either a 16 pin or a 14 pin dip. But you got to understand, these guys don't do that. They don't handle a bunch of power. And if they don't handle a bunch of power, we can get a lot of integrated circuits on a single wafer. But there's the exclusive OR, and then all these gates are in here to take inputs from another stage if we want to cascade them, and it gives us the outputs over here. But all it is just ANDs, ORs, NANDs, and ORs, right? And NOS. That's all it is. So but I don't really need to know this. All I need to know is I need to know what the chip does, and if it don't do what it's supposed to do, we replace it. I mean, I don't go in here and troubleshoot that NAND gate right there. I can't. So we don't really need to know what's inside. We'll talk a little bit about the different types of outputs we can have, because it's very important that we understand the outputs, what's actually driving it. And it'll help us in our troubleshooting. But as far as everything else that's in there, then we don't care. All we know is what we need to put on the inputs. So if it's TTL, we need to put at least 2 volts on it. But the outputs are guaranteed for 2.4. So that's what we're looking for. So for legal highs, we're looking for 2.4, right? You understand? Legal low, we're looking for less than 400 millivolts. And then we know this will give us at least 2.4 volts out of these outputs. And all I got to do is figure out, okay, how do I hook this thing up? So that's where you come into the data sheet and see, okay, how do I cascade these things? Because these are cascade inputs, which means what? We can feed this from another 7485. So instead of comparing two 4-bit numbers, we could compare 8-bit numbers, we could compare 16-bit numbers, 12-bit numbers. All we have to do is just go in groups of 4s. And we take the output of one and feed it into the next one, right? You understand? So yeah, it's a pretty neat IC. I think, I don't know, I can't remember at that Beech's machinery, I can't remember how many transistors I replaced when I put this one little chip. I used a wire wrap socket, by the way, but it was an offset, so the wire wrap came up. I showed you the wire wrap socket. Yeah, I did. All the wiring, yeah. Oh, he didn't? So prototype boards, when we start prototyping, of course we got breadboards, but breadboards are not, guys, I'll be there. So this is the way they start prototyping these things. Even these stuff like a 7485. So I guarantee a 7485 was originally made out of regular gates, and then they got it so it works, and they figured it out, and then they started doing what? They started shrinking it down. You already see some of the big blow-ups of microprocessors. They'll have a little thing up there like 7485 will be inside there, and it'll be a little square where they actually show the ICs that they're putting in there, but they're integrating it on one. They're integrating it on one way. What's that? Wire wrapping? Believe me, I've done a lot of wiring. I'll show you all the tools. We got another little technique called split wrap, which is a lot easier. The wire wrap, you literally have to strip. You have to have a little stripper, and you strip them off about 1 inch, and then you wrap it on there. Split wrap actually trims the inside for you.
What's the purpose? Is that not bare?
Yeah, it's bare right here, but you have to strip it off. So you got a little stripper. That's why I need to find my stripping tool to show you. I can show you. I'll try to find my wrap. I know where my split wrap tool is. Split wrap tool is a little easier because you don't have to strip the wire. It's got a little blade on the inside, and it strips off the insulation against the post for you. And it's real fast. I mean, you can rip around. And what's nice about this, if you make a printed circuit board, then it's made, right? You understand? If this one, if you change things around, then you just got a little thing you unscrew it. You just come back in the opposite direction, pull it off, and you can rewire it or do whatever you want. This is wire wrap. So that's what I put in that machine that I made. It's pretty. But they do math, so I can come up and I could look up I'd have to look it up. It's in y'all's next chapter. We're not going to get into there, but and all this is I don't know if it's going to give us. Wikipedia might give us a number. AAA adder electronics. We'll see if they give us one. A full adder, half adder, we've already looked at that, but I don't know if they give us a layout of that. Well, that's pretty good. That's an animated GIF. I like those. But yeah, we have adder circuits. So I think the next chapter, which we're going to split over, we just don't have time to get into everything. But I think the next chapter after exclusive board is math circuits. Yeah, chapter 7, which is on page 260. They teach they teach binary math, by the way, but they talk about 2's complement. We touched on that a little bit. Talk about hexadecimal arithmetic. That's real fun. Because you carry on 16. But once you learn how to do it, it's not hard. Then they get into full adders, half adders, and then the IC that they talk about is a 7483. So it's an adder. So it's got all, but it's the same thing. But I really don't need to know what's inside of it. All I need to know is how it works, right? I understand that. He says, like, we got a lot of people driving cars that have no idea how they work. To drive a car, you don't need to know how they work. All you need to know is that when I pass the, press the gas pedal, I go. When I hit the brakes, I stop. As far as the combustion engine goes, that you don't need, most people don't need to know how those things work. They just need to know what they do, right? So we can generate parity with them. We can generate, we can do math. We can do, they can generate parity. They can check parity. So we got circuits though that are parity generator checkers. I mean, that's what they do in life. So I don't have to use an exclusive OR. What can I do? Well, I can just go out and buy one. But it's combinational logic. All it is what? All it is nans and nors. That's all it is. That's all it is. But it's got its own symbol. Most of your combinational logic is the symbol. What did I tell you what the standard symbol for combinational logic is? It's the world famous rectangle. So everything we look at past exclusive ORs are going to be rectangles. It's up to you to either use the part number, or what you'll find out, you can identify it by the names of the signals, the pin. Normally you can see what it is. So are you okay on exclusive ORs? And exclusive NORs. I think Book talked about programmable inverters. So they call these programmable inverters, they call it controlled inverters. So we can either make it buffer, or we can make it so I'm gonna go on Blackboard real quick, and the problem is that most digital books don't teach this, but you're gonna run into them all the time. So we have the 5 basic gates, and they do logic, right? But when I come up here and look at some of our data, and it's going to ask you, one of your quizzes, it's going to ask you what's the difference between this and that. And so, all you got to do instead of guessing it is go and look at the what? Yeah, data sheet. Let the data sheet tell you what they are. But let's see if it's on here. So here's a 7407. And what does it say this guy is? A buffer. This is a buffer. Hex means there's 6 of them in there, right? You understand? Let's see if they show us the symbol. And here's the symbol. All it is an inverter without a what? Without a bubble. So these guys don't invert. What you get in, if you put a 1 in, you get a 1 out. If you put a 0 in, you get a 0 out. But we use them to isolate, to protect things. We put them on the input, and then if something happens, it gets your buffer, and it don't get your inside your logic. We use them to increase drive. What happens is that these guys can only drive so much. So if we look at the data sheets, and this is, by the way, this is the actual makeup inside, and we'll talk about it later on. This has what we call an open collector output. We'll learn out what that means. So this guy right here, every input of this is going to draw what? 1 milliamp. So that means if I hook 10 of them in parallel, that would require 10 milliamps, right? You understand that? But we look and see what they can put out. What's their low-level output? Yeah, their low-level output. So here's low V out low. They can drive what? 16 milliamps. So they can drive 16 milliamps and still maintain the output is what? At 0.4 volts or 400 millivolts. But we'll talk about later on how many outputs a gate can drive, how many inputs a gate can drive. Well, what happens if I use one of the output, if I use one of the loads on an output and then go to a buffer, then we get that many more, right? You understand what I'm saying? So that's what they're talking about. We use these for buffers. We use them for drivers. We can use these guys to turn on LEDs. We can do a lot of things with these that we can't do with a normal gate. But it's not an inverter. It's a watt. But the book don't really teach it now. Why don't the book teach it? Because it don't do any logic. It's not one of the 5 basic gates. But it's got a function in life. And we'll find out later on what these functions are. It's open collector. We'll have to learn what that is too. So that wasn't a really good example. This is probably a better one. So this is 7406. It doesn't have it does. It has an open collector out there too. Jeez. Let's see if we got a 7405. No, I don't have a 7405 up here. But that identifies, what the gate is. So if we come up here and look at this guy, the 70404, which is what we're dealing with, it says it's a watt. It's a hex inverting gate, but we call them inverter. So this guy does logic. So a buffer, you get a 0 in, you get a watt out of it. 0 out, and you put a 1 in, you get a 1 out, but it's got a function in line. It's just like when you take motor controls or PLC, a normally open contact by itself doesn't do any logic. Because when it closes, it turns it on. When it opens, it turns it off. So it's what you're getting in is what you're getting out, right? So it wouldn't be, so in motor controls or PLC, when you learn how to wire the 5 basic gates with contacts or switches, they don't talk about a single switch on itself because that's what we consider to be nothing but a buffer because it don't do any logic. So this is the one that we're dealing with right now. The 7404, and then what else are we dealing for? We're dealing with the HC04 and the HCT04. And we'll talk a little bit about these. These are CMOS. For years and years and years, if you saw 7400, it meant it was TTL. So we had a 7400 series and we had a 4000 series. The 4000 series was CMOS, and then the 7400 series was TTL. And the two was not compatible with each other. So you couldn't use a CMOS chip to drive a TTL gate, and you couldn't use a TTL gate to drive a CMOS chip or gate. So you had to go through what they call a level converter. You had a special chip that would do that for you. Well, what they did is they came out with the HC version. These are still CMOS, but these have the same pin out as the 7400 series. The 74HCT, these suckers are TTL compatible. So we can use these to drive TTL gates. So we can use HCTs and 7400s in a circuit together. So this really was confusing for a while, but for a long, long time when we saw 74 at the start of it, we knew TTL, but these are not. So they had a whole new series. The 40,000 series, by the way, is just about obsolete. You can still get them, but this guy right here has basically replaced the 4000 series. So you'll see a lot of 74HCs and you'll see a lot of 74HCTs because they consume less power. And we'll talk about the advantage later on. So we can add, we got parity. What else did we say we could do? They can do what we used to call programmable inverters. We can either make them act like inverters or act like buffers. We can make them generate and check parity. So these guys here have a lot of use. In math, right? They can do addition. By the book covers binary math. The book covers two's complement math. It covers a lot of different types of math that we just don't have time to get to in this class. And digital, you're not going to run into it that much. And in computers, you don't see that anyway because all these logic functions are done inside the processor, right? So the processor does the 5 basic logic. But it can compare, it can add. It can subtract now, it can multiply and divide. When processors first came out, they could only add and subtract. And you had to write programs to do multiplication, division, and square roots. But now most of your processors do that for you. So exclusive ORs and exclusive NORs. Good chip or good circuit. So any more questions on that? So that helped you on that a little bit. Now we're using a 7486 in our lab, and I think it's an exclusive OR. But so we don't have an exclusive NOR. So how would you make an exclusive NOR out of an exclusive OR? I'm listening, guys. So I want to take this and I want to turn it into this. What are we going to do? Nobody's got any idea. I'm going to come over here and do this. And now we got an exclusive NOR. So the lab kit doesn't have both these. They've got an exclusive OR. And then you're going to just add that inverter, and then you'll get the exclusive NOR function, but your output will be out here, right? Y'all understand? What lab are we working on? What lab are y'all working on? I need to go back and figure out the. So some of y'all are working on enable, disable, then inverting. This is where you're going to deal with your name. You're going to deal with your NOTs, your NANDs, and your NORs. Enable, disable. This is where we talk about opening and closing the gate, right? Where you use one input of an AND gate or an OR gate to either let the other signal go through or not. De Morgan's theorem. This is your Boolean algebra. But what we're going to do here is that you're not going to have to solve any equations. What you're going to do is you're going to wire the circuit up, and then I'm going to show you, I'm going to do the reduction for you, and then you're going to wire up the reduced circuit, and you're going to do the truth tables. And what you'll notice is the truth table for the big circuit and the truth table for the smaller circuit match exactly. That makes sense? And so, like I said, so this is our so see there, so there I did what for you. See, I reduced it down. And that's what you're going to do. So you're going to come up here and you're going to wire up this circuit right here. And then you're going to wire up this circuit. Then you're going to wire up this circuit right here. Right? You understand? So you know how to make a circuit. So what gate would y'all use that with there? Oops. Let me take off my capital lock. Let me switch back over. So we're looking for X is equal to not B and not C, right? So what would that be? So let's draw the symbol for that. So I'd come over here and I would put a what. This represents a what? What type of logic? And this says the inputs are low active and the output is what? High active. Of course, you can't buy one of these. You can't buy a negative NAND, right? So what would we use? Well, I'll push bubbles. All ANDs are going to complement to some type of OR. If it's got a bubble over here, I'll leave it off. If it don't have a bubble, I add it. So that's what gate you'll use to get that logic. So what we're doing, what we did, or what this thing right here showed us, is I went from this circuit to one OR gate, one NOR gate. So you can see all these are reduced for you, every one of them. So all you're going to do is basically just hook them up, not reduced, and do what? Hook them up, reduced. Then I think that's this one. Let me look at. It seems like we have another lab that's more complex than that. No, that's it. No, this is it, lab 7. So let me bring this one up. Or I'll try anyway. I hadn't had time to go wipe this out, but you're not going to need any of the resistors or the LEDs or anything because that's inside the trainer, right? I'll try to get that done. But see, here's a circuit, and then what they do is reduce down. So here's the procedures. That's the circuit you wire up, and see what I've done. What have I done for you? I've reduced it down for you, right? Then you're going to draw the circuit, and you're going to come up, and you should come up with the same truth table you got for the full circuit, right? So here's the circuit right here. It's done what? It's reduced down. And then what you'll do is you'll go through the same truth tables for your, but you'll have to draw the circuit or whatever you come up here. That looks like a real easy one. And then that's, I think that's all the reduction that has to be done. Just those 2 circuits. Some of y'all need to, to move up. Like I said, we're going to be in lab tonight, and we'll be in lab Thursday night too, because y'all are going to be in lecture next week, right? Y'all know the next 2 classes are going to be online, right? I'm sorry, next week's classes are going to be online. Huh?
17. Read Boston. You're living on 17.
Okay, yeah, the 17th. You got me messed up. Nancy's going to meet this Friday. So we're going to try to get as much lab done as we can before we do that, because we'll double up on lectures. We'll have to have another lecture before then. But so what we're going to do is we're going to go to lab tonight, and then we'll be in lab Thursday night too. We might have a lecture on next Tuesday, and then we'll probably be on lab next Thursday. And then we'll have 2 lectures the week after that, right? You understand? And then, by the way, not only are you going to have a lecture, you're going to have a topic quiz on the lecture too. And what I'll do is I'm going to make the lecture available all day long. So you got the whole day to watch it. And then when you get through, and that's the way I'm going to do roll too, once you complete the topic. Are you okay? Any questions? So we got quite a few people that's not here, but we can't worry about them, can we? So let's go lab.